So I'm Marcus, I'm a computer science professor, and I'm here today to talk a little bit about antiviruses. So more specifically, I'm here to do a little bit of propaganda of this paper that I published. I suggest you taking a look. There are more than 70 pages about antivirus internals. And the reason I published this paper and doing this talk is that I see many criticism about antivirus over there, and I agree with many of them, but I see that some of them are not very accurate because some people not really understand how antivirus actually work. Of course, not the case of anyone here, you're all experts. But I see many criticism, and I'd like this criticism to be fair so we can move forward to propose a new antivirus. So I'd like to demystify some aspects, starting by the fact that we should not confuse the antivirus engines with the antivirus products. Because the same engine might be licensed for multiple antivirus products, right? So it's very easy to see that if you kind of cluster all the labels provided by the antivirus, as we did here for multiple million samples submitted to VirusTotal over the years, we can see that the AV products cluster around the AV engines. And for some years, the AV products migrate from one cluster to another because they are licensing a different AV engine for that given year. We can also see very interesting effects like the merging of Avast and AVG, not only because that companies merged, but also because their engines merged as well. So the lesson here is that do not trust evaluations that simply count the number of antivirus detecting a given number of samples. These evaluations are counting the same engine multiple times, so they are introducing bias in evaluation, right? So this is not fair. Another aspect we need to understand is that antivirus have multiple components. And I see many write-ups over there claiming, hey, like I crashed the antivirus, but in fact what happens that like the GUI crashed, but the backend process is running. So the antivirus has multiple components, kernel drivers, libraries, backend process, all sorts of components. We need to understand them to make the fair criticism, and I will try to cover all of these components during this presentation. Starting talking about how to detect and not detect stuff. So I'd like to talk about the fact that whitelists are still very widely used, because sometimes people say that, hey, antivirus are good at detecting malware, or not are good at not detecting goodware stuff, not causing false positives, not blocking legitimate stuff. But if we look inside the antivirus, what we see in the reality is that they are basically, in many cases, using whitelist. You can find configuration files like this inside of your antivirus, saying that some given file or given process, as you can see here, for instance, for OneDrive, should not be blocked, right? So I'm not talking here about the user adding something to a whitelist. I'm talking about the antivirus by default shipping this type of configuration, right? And of course, this has implication in project decisions. So if we inspect the code of the antivirus, we can see that there are functions over there to perform whitelisting. And more important than that, this same function, if we found the location of the function that is scans file, we note that the function that is first invoked is the whitelisting function. Because the antivirus is checking if the file is in a whitelist. If it's a whitelist, it doesn't proceed with the scan, likely because it's going to take it to a false positive, right? So the problem here is that sometimes someone is proposing a model to detect some stuff and comparing against an antivirus. And this evaluation might not be fair because the model might be not so good, and you say, hey, antivirus is really good at not detecting this stuff, but the antivirus is using a whitelist and the model is not. So once again, you need to understand to make fair evaluations. In AVs, of course, not only they use this data, but there are companies out there profiting on top of that. So there are companies selling whitelist data, as you can see in many advertisements. I'm not saying that this is right or wrong. I'm just saying it happens. Antivirus collects lots of information of multiple scenarios, but they largely rely on whitelist and need to understand this stuff. And I need to understand the opposite as well, because sometimes the antivirus uses signatures to detect this stuff. And this is where there is a practical divide, because half of the people will say, hey, antivirus only uses signatures and nothing else. And other half of the people will say, hey, antivirus does not use signatures anymore. They use very sophisticated machine learning stuff. And of course, the truth is somewhere in between, right? Of course, antivirus uses signature. I have an example here to show you. So I'm creating a text file here that's basically some IOC, some shellcode in text, and then I'm copying this from the remote location to the machine that has the antivirus, and I'm going to force a check of this file. And what you are going to observe is that this check shows that the antivirus actually detected the content of this file as being malicious, right? When it should not, because it's just a text file. It's not an actual PE file, but it's detecting, as you can see right now. So the only reason for detecting this type of stuff is using a signature, because if it's not an executable file, you cannot say there is any type of dynamic analysis or emulation taking place. So of course antivirus uses signature, But the question is, to what extent they use signatures? And I try to discover. And to do that, I create an algorithm based on the binary search problem that basically is the following. For a given file that I believe that's detected using signatures, I create a copy of this file. And then I patch the two halves of the file. First half in the one, second half in the following. And then I submit it again for the verification. And if they're using signatures, one of these half it will be detected by the antivirus in this new query. And then I repeat the process, keeping split these small steps, small patched parts in two and two and two over and over again, until we identify what's the minimum pattern of bytes that are detected by the antivirus. And then we claim this is the signature, and we can identify what's the size and what's the prevalence. And it's interesting because if we do that, we can find very interesting stuff. For instance, what the signature is being detecting. Of course, for many cases, it's just a blob, a bunch of bytes in the file. But for many files, we can see that the file format is being detected and even the entire executable file, so we can have an understanding of what the signatures are detecting. For some antivirus, you can also see interesting stuff that different antivirus are using the same signatures, exactly the same one, as you can see in the hash. So the antivirus, in some cases, are not only sharing their engines, but they're also sharing their threat intelligence. So they are sharing the same signatures over multiple products. They are detecting exactly the same stuff. But to actually answer the question, of course, the results vary from AV, but our result says that from a 30% of all detection to 40% of all detection are performed using signatures. So the good news for the attacker is there's lots of room here to apply the usual techniques, polymorphism, mutation, and so on to evade antivirus. But the good news for the defender is that, well, more than 50% of all detection is not performed using this simple signature anymore. They are using other mechanisms, either machine learning, heuristics, reputation, something that is supposed to be more robust. So we are making some progress, right? And of course, the signature size also varies. So we have here results for many antivirus. Some of them use smaller ones, larger ones, but in average, they use a little bit more than a few kilobytes per file to a little bit less than 1 megabyte, if we consider this whole experiment. Some of them uses more. We have here like 10 megabytes for someone, but not put much focus on that, because what happens here, in fact, is that the regular expression, that is a signature, expanded and matched the entire section, including the padding, so it identified the whole pattern. But for the most case, it used a little bit less than 1 megabyte, and majority of the case, only a few kilobytes. And this is very important if you are evaluating some solution or developing a new AV, because it informs how many signatures can be delivered via an update of the antivirus, or if you're going to design an AV, how much storage do you need to store all this amount of signatures? Now you know what's the size. But when you talk about detection, it's important to talk about trade-offs, because sometimes the AVs do not detect stuff, not because they do not know to detect, but they somehow chose to do that. And the packer is a good case. I mean, packers have been there for a while. We know more or less how to handle this stuff. But if we investigate the antivirus, we notice that each antivirus supports a different number and different types of packers, in the sense that they have different components to identify these packers and to unpack these packers. And the reason is not that we as a security community do not know how to unpack or to handle packers, but that they believe that their product is better used in one solution than another, or that a given scenario is more likely to be targeted by a type of packer than another, so they put only a few types in their solutions. To show that case, we can see the case of UPX. That's a popular packer. We all know that. It's open source. Everybody knows how to unpack that. And we did the following experiment. We tested the detection rate of the original samples, of the same samples packed with a standard UPX that download from the internet, and UPX samples in a custom version that we compiled from scratch. We got the source, modified UPX, so you only can detect these files if you actually unpack these UPX. And the result is, for some antivirus here in the beginning of the graph, we see that they only detect the original sample. No UPX sample is detected. So the reason is not that we as a community do not know how to unpack that, but that these antivirus decide not to support UPX for some reason. For the majority of them, they detect the standard version of UPX as well, but not the custom one. And only for a few, on the end of the graph over there, they have unpackers implemented inside the AV, and they support that. So it's important to have that in mind to make a fair comparison when you are claiming some stuff or not. We have to understand what were the project decisions. Once again, not saying this is a bad or good decision. I'm just saying decisions are made, right? We need to be fair. Once again, talking about be fair, detection not only occurs statically, but sometimes dynamically. So when you are executing, they also collect information. And it's interesting because if you get a process and enumerate the functions, the libraries loaded inside your own process, you have a code here to try yourself. You can see that sometimes there are some strange library inside the memory of your process. There are, for instance, the case of the antivirus library that you can find over there. And these libraries are used with a hooking mechanism. These AVs usually use custom hooking mechanism. It's very rare to find, popular hooking solutions over there. Each antivirus writes their own. So basically, they hook into functions to collect data from these functions for classifying stuff. It's interesting to see that the amount of functions hooked by each file, we have identified all of them for different AVs, as you can see here, varies a lot. So some antivirus hooks only a few ones and other lots of one. So if you hook only a few ones, you have a narrow view of the system. And if you hook many functions, you have ability to collect more data. But you also have another drawback, because if you hook too much functions, you have too much interposition code to run, so you have lots of overhead imposed in the performance. So once again, it's a trade-off decision. Each antivirus decides a different way. And here I see many of my colleagues that are designing new antivirus, making once again unfair comparison, because they say, hey, I create a new machine learning model for online detection, 99% accuracy, but this model hooks like 200, 300 functions. And they are comparing against one of these antivirus. So this is not a fair comparison because they do not have the same amount of data, right? I'm not saying that their proposed solution is good or that antivirals are good solutions. I'm not saying anything like that. I'm just saying that the comparison sometimes is not fair. So we need to understand how these antivirals actually work to make fair comparison, to make fair criticism, and then to make them to evolve. To be fair with them, they do not collect information only at the user land, they also collect information at the kernel land. So if you inspect all these antivirals, you can find for all of them multiple drivers that performs lots of information gathering via callbacks for processes, register, file system, network interposition, for all this type of stuff. Sometimes they use that for some detection, but the most common use case for that stuff is self-protection. The antivirus is trying to protect yourself, like trying to prevent you to go to the location where the antivirus is installed. So if you try to go there, you get access denied. Who does that is this type of driver. And here there is an interesting experiment, because if you try to enumerate all these locations in your system, accessible locations, with and without the antivirus kernel drivers, you can identify what are the locations that the antivirus drivers is protecting, is denying access, right? So this is an interesting reverse engineering hint for you, because the antivirus is kind of revealing to you what are the important locations for the antivirus, what are the locations that the antivirus are trying to protect, that it stores its critical files. These are the locations that we identified. You can do that for any antivirus, identify what are the locations. Besides that, antivirus also spy on your network. Of course, I'm being provocative here because they have to inspect your network to do that. But to do that, they perform interesting stuff. So for instance, if you use Kaspersky, you have this AVP process that is the antivirus proxy. So basically, all your connections are redirected through this process, and this process actually scans the network connection. This is an antivirus process that scans what's being trafficked. So if you take a look at this screenshot, what you notice is that the browser connection does not appear in the screenshot as originating from the browser, but from the proxy server, because the browser connects to the proxy and then the proxy goes to the internet. To do that, they have to perform a kind of a man-in-the-middle strategy against the user. In this case, the user accepts the agreement, so I'm not supposed to say that's an attack, but basically the technical knowledge behind that is the same. And to do that, they install a certificate, an AV certificate in your browser to allow HTTPS connections go through the proxy server. So if you access a website when you have an antivirus of this installed, and you check the certificate for the website, you can note that's the antivirus certificate and not the original website certificate in most cases. Some antivirus, they are rare, but they sometimes do different stuff. Like the Viper identified, they use snort rules, so they use a subset of snort inside the antivirus. But the rules are there and clear, so if you do some reverse engineering, you go there and learn how to evade this stuff. Or I'm supposed to say, learn how to improve the rules. But that's what happens. After detection happened, the AV work does not stop there. It keeps working, storing files in quarantines. The files are not immediately detected. the files are stored there. And the reason is that the user might regret the antivirus decision and say, I want my files back. So what you find in most antivirus is a configuration file like this saying, hey, this was the original file location, this was the file name, the file attribute, and this is the new one. So the file is now in this new location with this new file format, with this new attribute, so the antivirus can recover and restore. And basically what the antivirus does is to encode the file in a different way. It's not a PE file anymore, so it cannot run and not infect the system. I infected the system on purpose and checked what is in quarantine for some files for this one. And I got surprised that the file is not actually encrypted. It's just encoded. So you can see the file size is the same. And in fact, what happened is that for each byte that you have in the original file, you can see this is a PE file. There's a MEZ flag over there. Basically, what you have later is a mapping for some other bytes in the file. So it shows that we can decode these files and get the files back. So if you have access to an antivirus over there, you can go to the quarantine, decode the quarantine file, and get pretty new malware samples for your analysis. Some antivirus are charging for doing that. I suggest you, you might not pay if you are able to decode that. Let's put it this way, right? There's no need to do that because in most cases they are not using any encryption, just encoding. Besides storing this file, antivirus stores lots and lots of files about your system, about you, in many databases. Many of the data is used for telemetry, for some kind of feedback for the antivirus, reinforcement learning, whatever the antivirus is doing. And the side effects also collect information about you. So if you look inside the antivirus, you find like databases like this, collecting all sorts of information, like which files are scanned, when they are scanned, all the timestamps, what software is installed in your machine, all this type of stuff. And if you go to a live system running this stuff, you can actually get this information from your system over here. As you can see, there are multiple processes, what's been happening from each one of these files or process. So many people are paying very expensive solutions for monitoring with beautiful graphical user interface. Okay, you can keep doing that, but if you prefer to do something more open source, built from scratch in-house, maybe you can do some reverse engineering of antivirus and just discover where these databases are located, and then you can get information from there. This information is very useful, right? So don't need to pay anyone to do that. You can do it by yourself as a good hacker. Another reason for storing all these databases is caching, because lots of the antivirus performance depends on caching. For instance, antivirus has caching information, because if a file was scanned, this file is not scanned over and over again. This file is scanned again only if the file is modified. So the antivirus keeps track of this information. And the same is true for URLs, because users tend to access the same website over and over again. So they scan once and then keep this result valid for a while, time to live of this scan. It increases the throughput because some files are skipped, so the antivirus can scan more files in the same time frame. The problem here is caches can be exploited, of course, for offensive security purposes. So here I show the case where we have, a malware that is divided in two. So we have a loader and we have a payload that is decrypted in memory. So if we put the two files over there, what happens is that the antivirus emulator, you try to run the loader with the payload, and you identify that the loader is trying to load this payload, and you detect that. Right? So basically, I'm showing basic information, and it will detect that. What I do after that is to put this separatedly. So I first put the loader, right? Here's the case where the antivirus is detecting the original loader. But then I do different. I put the loader over there and let the antivirus try to scan. The antivirus emulator, you not find the encoded payload, right? Because the payload is not over there. And then you cache the information that this file was clean, because since the payload over there, the loader wasn't successful in its execution. It could not load the payload. And it stores in the cache like, hey, this file is clean. And then you move the payload over there. And then the antivirus try to check in the database if the loader was allowed to run or not. It was allowed to run because a previous scan cache said the file was clean. But now it has the actual payload, and then you see the result. The message box was displayed because it was able to run, right? So you can exploit the cache for malicious purpose. Other stuff that you can take a look and exploit is like antivirus update, because antivirus updated a lot. You can see here I have been tracking a real antivirus system for like 30 days, 24 hours a day, and you see how much they upload. Sometimes they upload multiple times a day. But what's interesting is that how these uploads occur. Because for some antivirus like Avast, you can see here, it downloads its virus definition in clear, like plain HTTP, no HTTPS. I don't know why they did this project decision. Maybe some legacy compatibility, I don't know. But they do that. And since they do that, we can do, once again, the man-in-the-middle strategy. We can go there and collect what's being downloaded from this antivirus. And we see something like this as an antivirus update. We can find something more or less familiar here. Like in the beginning, we have something that looks like a header of the antivirus. And somewhere here, we have, once again, the MZ flag that suggests that there is a P file inside this structure. So to put it in a different words that we all hackers understand a little bit better, basically what happens is that there is a header of antivirus, there is the content, the actual payload, and there is some signature, some verification, because since the payload is trafficking clear, they at least add some hashing and some signature to the file to not accept any tampered content. So they verify if the content they are receiving from the network is signed by the antivirus. But the important lesson here is that since they follow this known structure, basically we can get the upload, the updated, the signature, the database update from the file. So that's basically what I did here. So I parsed the original VPX file that is the update, and then extracted the P file, checked the signature, and get, well, what's being deployed, delivered in this updated, and what's being delivered, you can see here, is a DLL P32 plus 64 bits, right? So the lesson here is that the antivirus during the updates are not only updates, signatures, classifiers, stuff, whitelists and blacklists, they are also updating the antivirus software itself as part of its updating strategy. And it's interesting because update is a critical process because you are changing parts of the antivirus, and antivirus largely depend of their integrity. If the files are not integer, the antivirus will not run. As I demonstrated here, crashing a little bit the antivirus. So it shows once again that you should worry about that because sometimes the antivirus might crash and not tell you. So depending on how the antivirus crash, you not notice that because the tray icon will be there, but the antivirus will not be running. It is important to pay attention to aspects like physical security. If someone is able to boot your computer in safe mode without the drivers that's protecting their location, someone might go there, tamper the files, delete the files, do some kind of crazy stuff, and then antivirus stops. So this is part of the antivirus threat model that's not often clear. Other threat model decision that's not often clear is that the antivirus depends on pristine installation, which means the antivirus supposes that the antivirus will be installed in a clean system and infections will occur only after the antivirus is installed. The antivirus assumes that, but the antivirus company did not make that clear. And I would like to make that clear. Because what happens in reality that most users, will be running their computers, you'll be infected, you notice only after the computer starts to slow down. And then you go to some internet forum and some random guy, you say, hey, use this antivirus because the antivirus is good. And the people try to install an antivirus in a system that's already infected. And this tends to not work well, right? As I show here. So basically what I did is to first create a kind of a malware that's very simple. It's just an infinite loop that's checked for no antivirus location, no antivirus folders, and try to remove everything that's there. And then there isn't the antivirus installer trying to install itself in this system. So there's basically a race condition between the malware and the antivirus. And what happens is that the antivirus is not able to install in the system, right? So for antivirus working, they assume that the system, is in a good state. It's a pristine installation. They cannot guarantee that they can work if the system is already infected. But this is not often making clear, and I think it should. And it works for Avast, and it works for any other AV. Basically, we crashed all of them. You can read all details in the paper. Beyond that, there's also other components of the AV. As I mentioned, there are browser extensions. So if you remind the first figure about the components, we have a kind of a client-server architecture where all AV components connect to a backend server of the AV that actually process the detection stuff. So we can see that basically in your browser, there will be extensions that use the browser capabilities to make HTTP requests to connect to the antivirus backend. So the antivirus backend has a small HTTP server, receives requests from the browser extension that's collect information about the pages to scan these pages. And after in the future, the antivirus provides a response, and then the same extension might do any stuff with this result. For instance, redirect the user to other pages. So the user will see that notification that, hey, this page might be compromising your system, all this kind of stuff. This is basically done this way, just, HTTP request, changing the headers based on the result that the antivirus process provided to the browser. There are other components. In this paper, we analyzed the Windows, Linux, web, Android, AVs, all sorts of AV. I decided to finish talking about Android because this is the most concerning situation, because in comparison to what I presented so far for desktops, Android AVs are much, much simpler. They are largely relying on Google Play is doing a great job, and they only do extra, small extra checks, cosmetic stuff to say so. So, for instance, they add some databases to your system to avoid someone, receiving SMS for a given number or to receiving call for that number. There is no on-device verification. So there's basically, reputation-based, externally updated. So you have to, trust that these databases will be reasonably updated over time, because there is no other capability. More than that, their detection capability is also limited, so you can see large whitelists like these inside the antivirus. So when they are trying to install some software, what this antivirus for Android are doing is just checking if the file is known. If it's not known, it raises a warning like, hey, this software might not be good for you, but it's known, it's in the whitelist, it doesn't complain. So they are here changing, security verification by reputation. Because they're saying, hey, if all these software are very popular, they are safe for your machine. If they're not popular, they're not good for your machine. And we know that this is not a good trade-off, right? One reason for that is there is, small sources of data collection mechanism in Android. It's very hard to load kernel drivers in Android. Many antivirus do not have any kernel drivers, any libraries. They cannot do that. Some stuff would require, rooting the device, which is not good for security in the sense, so the antivirus not to do that. So they have a limited ability to capture information about the system. So that's the reason they are limited in this sense. So the point here is that lots of research that can be done in this direction to improve this stuff. What they have been doing so far is to abusing existing service, like accessibility service. So they are hooking to I/O mechanism, creating fake keyboards, or adding overlay to the screens to collect information. So they collect information like from pages that you are accessing to notice that, hey, this looks like credit card number or this kind of stuff. Well, this is very limited in detection capability, and this also makes the antivirus to look like the malware, because there are many malware that do the same stuff, abuse accessibility service, add overlays to your system to collect information. So we can do more research to improve the situation, right? So what we do now that we know all this stuff? Well, basically, I believe there are a few things to be done. That first, I think the AV companies should, be clear about some decisions that they make about the threat models. Sometimes this is not clear for the users, or sometimes even for experts. I think we as a researcher should understand better how these antivirus work to make fair criticism. The goal of this talk is not to say anyone to stop criticizing, is to keep criticizing, but let's understand very well what you are criticizing to make, as a result, have, a concrete direction, how to move forward, how to enhance antivirus. Lots of research should be done to enhance antivirus, right? Especially in terms of evaluation. In my view, AV's evaluation are chaotic. So, they do not evaluations antivirus in all these dimensions. They just say, hey, the detection rate is this one, and this one is not a complete evaluation of all the phenomena that I have been presented. So we can enhance our antivirus evaluations and compliance as well. As I mentioned, I'm a computer science professor at Texas A&M. What I do is cybersecurity research over there. So I create a new antivirus, and I use all this knowledge that I presented to propose new stuff, like new antivirus, hardware support for antivirus, new architectures for antivirus, and sometimes break stuff. So if you are interested in doing this type of stuff, let me know. Thanks for your time. Thanks for hearing me. If you don't have anything better to do and you want to do a PhD, reach me out. Thank you.
Thank you, Marcus. So we have times for a few questions. If anyone, yes.
How likely is it that machine learning is just going to become an antivirus and malware?
I think it's becoming antivirus already. Many people, many companies are claiming that. The problem is that what I noticed that it's very hard to transition a machine learning model, a very powerful machine learning model, to the actual product at the user land side. What many antivirus companies are doing is to use machine learning at their backends and then making this machine learning model generate the rules that are used by the endpoints. This is interesting because it's a very effective strategy in terms of performance. I think to move towards the endpoint, we need something better, some kind of breakthroughs to allow more processing power. And that's why I believe that the hardware takes place. So I think coprocessor, hardware extensions, all this kind of stuff might help. So if you have extra support for that, maybe we can apply this machine learning stuff for this antivirus. Yeah, probably. But of course, we need to take care about other aspects. For instance, I'll talk some other stuff that I researched that is, it's not only a matter of creating a machine learning model, it's a matter of how to make this machine learning model, working for a long time. Because there will be adversarial attacks, so there will be evasion. So how can you keep this model working? There is a known problem called concept drift. That is basically the model losing accuracy over time. And you have to retrain your model periodically. What's the best way to do that? This all happens in the back end. So in addition to the problems to transition that to the endpoint that we have, there's also back-end problems like what runs in the antivirus cloud. There's lots of research to be done there to make machine learning practical. Many antivirus companies are already running this stuff, but they are, far away from the state of the art in this sense.
Any other questions?
What do you think about AI machine learning with malware? Do you think that it will turn into a sense of using its neural network that the malware will then be able to transform itself to evade the antivirus?
Yeah, this is what we research most right now in academia. That's called adversarial attacks. That's basically ways to evade this stuff. Because we think of, I always say to my students that, malware stands for malicious software. In the end, you want to classify what is malicious. But this is hard to do. We don't know how to classify if something is malicious or not, because it's a human property. So in the absence of a criteria to identify what's malware, what's malicious, we classify what is software. So basically what we do is to classify the shape of the malware. So it's of course the shape of the malware is not the semantic of the malware, so it's always possible to evade. When you use machine learning, you're doing statistics. We have all these samples, and these samples look like this. They fit this probability function. So basically, if you create malware samples that are malicious to the human understanding, but do not have that function shape, well, they are benign for the model. So it's always possible to evade. There are deterministic ways to evade machine learning model. That's the gradient descent attack, right? So this is a problem. Of course, I don't think that we should get rid of them. They're important. That's the best that we can do. But you should understand the limits of that. So this is the state of the art. Automatic ways to create that.
And then I would assume that if you would have some sort of machine learning antivirus, that then you would also need a pretty heavy GPU to run it, of course.
Yeah. For instance, you might have a GPU. So Microsoft is moving toward that direction. Defender and Intel, they have a partnership to do that. But maybe you can find, an easier solution. Maybe, we don't need to put the entire machine learning model that we can kind of distill the machine learning model in something that is small and run there. Because as I said, antivirus is a complex piece of software. So you have signatures, you have machine learning, you have cloud detection, reputation based. So the strategy here is not only the detection method, but how do you orchestrate all of them? Sometimes it's better to have a signature, like for one day attack. You do not have time to train a machine learning model. Signatures are good for that. But for the long term, signatures are not good. You have to move to machine learning model. So it's a matter of a complex engineering process. Where do you put your detection in the multiple steps of a malware infection? And I think we should do more research in this sense. There's no one-size-fits-all solution. It's a set of solutions.
So AI is not going to be the savior of antivirus?
I think there's no solution for that. I mean, AI will be an important component for antivirus as it's an important component for everything. Like, people are not saying a lot about AI right now with the emergence of all this ChatGPT and all this stuff. What I believe is that, sorting algorithms are amazing, right? Do people discuss sorting algorithm like quick sort, bubble sort, all this type of stuff? Do not. They just assume, these are, the foundations of computer science. We use that. It's like for antivirus. Everyone knows here's signatures. Signatures are important. We just assume they are there. So I think, AI is already in UB our tool chain. So this is another tool that we can use. But there's nothing specific about AI, and regardless that. This is useful. This is important. It has pros and has cons. It's our goal to find where it's useful. But it's just be part of our tool chain.
Have you tried to train yourself into an AI model yet?
Yeah, lot of self-propaganda once again. So Microsoft, Endgame, and other companies have been running since 2019 antivirus evasion competition. So they create machine learning models that are used by these companies and make people to run. So if anyone wants to try, you can go to mlsec.io and you can participate of that to fool the machine learning models. And I'm winner of the 3 first years, consecutive years in a row of the competition. Yeah. So, basically, machine learning is good, but machine learning can be broken. Thank you.